streaming.
Okay. So I switch to my presentation. Wait a minute.
Okay. Let me make sure that we are actually streaming first before doing anything for real. There we are. We are streaming. Okay. You can begin. And I'm only 5 minutes late. Fine.
Not much time.
Not bad for today. And I'm going to be running around a little bit, so ignore me. Start your presentation if you're all set.
Okay.
Yes.
So, okay. Is everything visible? Oh.
Ignore any feedback from me. I'm turning off the mic so we don't get feedback from you talking to me talking.
Okay, fine. But the presentation is now visible, or is it not? Okay. So I want to present my instruction set architecture, which I developed quite for 8 years now. And yeah, it's a modified Harvard architecture. Sorry, my English is not so good, so I hope or you can understand me. Yeah, it's a word and address size agnostic ISA. That means that the instruction encoding and the encoding of immediate values doesn't depend on the word size or the address size. So are independent of the chosen address or word size, the instruction encoding remain the same. That's a little advantage against other instruction set architectures, because their encoding change with the word size or with other dependence of the word size. It have a single packet operation code format, and features a very extreme compact encoding, somewhere about 0.8 to 1.3 bytes. Some for common instruction sequences, and I think that's very compact. Multiple operation sequences are combined to a single unit of execution. That means simply instruction fusion. Yeah, this is a key feature for the high performance, independent of the implementation. So the ISO is from the ISO side, it's possible to allow very efficient implementations for broad scale of devices, from software implementations up to FPGA or ASICs. It's multi-core. We have some kind of multi-core support for up to 1042 processors with a common shared protocol at each cage line. So segmentation and access of internal and external memory is somehow synchronized independent of the core functionality. I want to explain this further, but this allows very efficient arrays, processor core arrays, which can share shared memory. Okay, and it's a misprocessing model applied there because all of the instruction fusions can be executed within a single clock cycle. I plan to publish this instruction set architecture with a non-profit license, and I haven't yet decided which license I can use, which is appropriate for this either. History is a bit special because all this began with Ngaro. Ngaro is a von Neumann architecture and a virtual machine based base for reservoirs from 10 to 11. Let me show this. So there's a homepage here for retro. It's the main grammar here, Charles Schilders, and here we have retro. I think it first began with retro 10. Yeah. We have here two implementations at current. Retro 12 is a current one. Retro 12 is the actual one, was is implemented on a new virtual machine. And yeah, I started patching the virtual machine layer of RetroForce and wanted to optimize it for more performance. This lead to is this here, sorry. Ngaro have some disadvantages. It's memory inefficient because each memory word is either an instruction or immediate value. The current VM engine solves this. The CISC-like instruction encoding lead to a higher effort for just-in-time compilation, and this was the main factor for me to start picking alternative virtual machine for RESO. It's not really suitable for efficient interpreters because comfortable for efficient interpretation. Because the dispatch overhead for interpretation is a main struggle for performance, and as much instructions you can execute within a single dispatch, as much performance and interpretation can get you. It features, in addition, variable instruction sizes, which make it very hard to program a just-in-time compiler for it. And it features only a single data format. We have no support before for floating point or even for vector processing, which were quite important. My first solution was to extend this virtual machine. So I combined a standard Ngaro VM with a simple ahead-of-time compiler, which was able to compile Ngaro code sequences to native code or direct reading code streams. The compilation was microcode for extending the instruction set at runtime. The either for this was an accumulator store design, a bit influence from early microprocessors like the MOS 6502. This only required changes of the VM sources, not of retro itself, and yeah, it was quite fun to implement. However, The advantage was a real performance boost, a real high performance boost. It was able to efficient compile the Java applications to native code and execute this compiled machine code quite comparable to compilations with a GNU C compiler, which I think was quite surprising. So this accumulator store design and the microcode approach lead to a very efficient compilation for superscalar out of order processors like Intel CPUs, the recent Intel CPUs, for example. But anyhow, I recognized some large disadvantages. The accumulator store approach, for example, is not really well suited for typical in-order RISC processors. Generated machine code was quite bad, and I found not the time to implement more optimizations, which was quite difficult to apply. I extend the base instruction set with somehow of more than 100 additional instructions. And this lead to a larger porting effort, sorry, for the native code compiler, and make it very hard to port the whole virtual machine to other processor architectures besides the standard Intel architecture. And the memory inefficiency was not solved because the Ngaro code was recompiled, and Ngaro code itself is not very memory efficient. My AOT compiler had still no support for different data formats, so I was only able to somewhere efficient compile integer-based Ngaro code, because that's all what was there. Yeah, and I have also no feedback from others, so that was a dead end for me. I doesn't found the time to develop this system user, but I start thinking about an alternative design, and this alternative design lead finally to as a Niagara-izer. We do require, in my opinion, a general purpose izer, which is efficient implementable as interpreter and as compiler. Reader itself require that different data formats are supported. Yeah. Simply from my own applications, which are based on virtual access time for satellite analysis and satellite data format analysis, I've had the requirement for floating point based computations, and this was really hard to implement with the standard reader system. I decided to base the izer on a fixed packet instruction format, because this eased just-in-time and ahead-of-time compilation on the one, and also simplified the whole interpretation effort, because it's a packet data for a packet instruction format is very well suited for combine instruction to instruction bundles and execute instruction bundles instead of single instruction with a single interpretation dispatch and execution cycle. This allows in addition, very efficient hardware implementations. I experimented with FPGAs, and a friend helped me to find a solution for some ASIC designs, experimental ASIC designs, which were very successful. Sorry. So Niagara started as a research project to implement these goals earlier. Yeah, Niagara is a word-site agnostic ISO. That means independent of the chosen word sites, the instruction set remains the same. The instruction encoding does not change, and the encoding of immediate values is not affected. I will explain this later, how this is possible. Possible word and address sizes are listed here. The word width can be chosen from 16, 64 up to 2065-bit, and the address width can be selected between 14, 24, and 64-bit. And you can here see the area size in byte, the resulting total memory which is accessible. Oh, I think that's an artifact. So the memory model is very simple. We have a single linear address space, and this address space is separated in a code area and a data area. Memory addresses are generally in signed magnitude format. Negative addresses address the code area, positive addresses the data area, and as you can imagine, the code and the data area are exactly half of the complete address space. External memory is not direct accessible, can be implemented separately. So the DMA controller, for example, or other possibilities. But all of the addressable memory is internal in the sense that it can be and should be implemented as SRAM. So if you can imagine that with a word size of 2065-bit and the address width of 64-bit, the resulting address space is not really implementable at current. So the ISA subpart no segmentation, very important, no paging and no different access modes. I decided not to waste logic functionality for this kind of otherwise implementable functionality, because memory protection and different memory models are equally implementable within a hypervisor and software. The Singularity project from Microsoft, for example, shows this very clearly. So I decided to use Retro 12 as hypervisor and extend the source base in the sense. So the register set is very very simple. We have not much registers, only 9. You see that some registers are not defined exactly, but depend on the chosen word size. That's the DS, the ARIS register, the TR register are dependent on the address size, and the IP for the instruction pointer, of course. We have here some special purpose registers. That's the DPs, the RP, here the pointers to the second data stack element, and the pointer to the second address stack element. These are the pointers for the stacks, for the return stack and the data stack. And then we have two cage registers for the top element of both stacks. Yeah, that's the TD and the TR register. And finally, we have shift registers here, which are used in between decodation. There's a CR and IR register, which I explain also later. Basically, these registers are used to hold a complete instruction sequence and allows very rapid and very low effort decodation and sequencing of instruction, including the bundling, which I also explain later. So the operation code format is something special because we have a fixed operation code width that's 64-bit, and the first 23 bits are the control sequence, selecting the functional units which are encoded, and the instruction sequence with the instruction for each unit which are executed. You see here something, a special slot, that's the IRAP slots, the last one, which is of 4-bit. The others occur only 3-bit, and the IRAP slot decide the repeated execution of the whole sequence. So it is possible to execute small sequences or operation codes repeatedly or dependent on specific flags. So operation encoding is also special because I decided to decode the instructions and the units in gray code because some recent research showed that the logic effort for decodation of gray code is more reduced to the standard binary encoding. And that's something of a bit optimization for ASIC, which allow lesser circle write and lesser complexity and also better power management. It's simply a micro optimization for real processors, allowing a lower circuit count. We have here the control sequence. Have I said that my English is at the moment quite bad? I'm just married, so I hope you can understand me. Anyhow, the control sequence here decode 4 functional units: ALU, arithmetic logic unit, memory unit, the stack access unit, and conditional and non-conditional branches. And here you see the instruction sequences that for the ALU, addition, subtraction, multiplication, and so on, arithmetic shift left, arithmetic shift right, and 2 binary operations, which are it's limited but appropriate for implementing all kinds of logic operations. Important here is the memory and the branch slots because memory operations are somehow restricted to fix the slot positions. Those are only restrictions for combining the units, and branches are special because I decided to implement no conditional branches, but combinations of skip instructions, comparing flags and the B operation for unconditional branches, BS for branch subroutine, and BR for branch return. That means zero flag, non-zero flag, equal flag, greater than or lesser than flag, and these combinations allow, I think, sufficient conditional control of the otherwise sequential program execution. Okay, we have here two NUB instructions, also no instructions. The first is for the repeat slot here, the IREP. It must be somehow signaled that operation code doesn't need to be repeated. And then we have here the no operation for the memory unit, simply to signal that some slots can be ignored. The control sequence allowed immediate encoding in the way that if you choose here one of the load store instruction or the load immediate instruction, then the following control sequences signal the width of the immediate operation, and also the instruction field are ignored, but instead encode the immediate value. So this allows, in a very efficient and compact way, the flexible encoding of immediate values within a fixed operation code worth. There are some pairing rules, restrictions for combining operations or instructions. First, the number of memory lots is restricted to 3 per operation code. Otherwise, processor implementations in hardware were simply not efficient possible. Yeah, the number of memory stores is also restricted to 3 per operation code, and memory lots are automatically prefetched and thus are restricted to the first 3 slots. Also, memory stores are performed always after the sequence execution. They finalize the sequence execution and are as such restricted to the slots, to the last slots before the IREPs load, that are these 3 one. So the first 3 instruction slots can either encode arithmetic logic, instruction set, memory operations, stack operations, branch operations. But if you choose the memory unit, only the first 3 slots can be selected, and also only the last 3 slots before the IREP slot are available for store instructions. I hope you can understand me somehow. Okay. It is possible to change the processed data format at runtime, and processor implementations are free to implement different data formats categorized in specific levels from 1 to 4. This allows simply special purpose processor implementations for specific applications. Because the logic effort was in general the implementation efforts, of course, grows with a number of supported data formats. And I want to ensure as much flexibility in implementation as possible. Data format processing is also really simple. Each processor implementation can implement each level, 1 to 4. The instruction set remains the same, independent of the data format. All data formats are processed within the same data. So if the machine code selecting, for example, the packet signed fixed point vector format, then the entire data on the data stack is interpreted, followed in this format. There are no conversation done. So, how is this either executed? Principle, we have 5 steps which can either be implemented for software implementations within a software pipeline efficiency or hardware with a 5-stage pipeline. A simple pipeline, it's an in-order pipeline, so you don't need superscalar pipelines or something, or an out-of-order processing. That's simply result here from the operation code format, because that's quite similar to very large instruction word processors, and I don't know if any instruction very large instruction word processor will be able implement superscalar out of order architecture, because it isn't required. Yeah. It doesn't make sense. So with a single 5-stage pipeline, you can get enough bandwidth for efficient implementation. The first step is the core synchronization, because they either support up to 1024 processors which share the internal memory. So some time of core synchronization, which is for real implementations quite special and quite complex, of course. But I have done it, and it runs well. As the core synchronization is required because the up to 1024 processors need to be synchronized for their memory access. So that's the first step, which is a pipeline. The next is a fetch, and third is a decode. Steps which are quite simple, because the fixed operation code format allow very efficient decodation with really less effort. So control and data stream generation mean that the whole operation code is transformed independent of the implementations as a compile an operation code to native code before execution, or compile them to direct treated code for an interpreter. And for a real hardware implementation, the up to 3 at current operation codes are decoded to internal control and data stream. I explain this quite in a minute. So the first implementation is an interpreter. So we have a core synchronization, is a violation, which is required, quite similar probably to the Erlang VM, for example, which allows soft real-time applications. The algorithm can be implemented in quite similar manner. We have a fetch, so the operation code is loaded from memory. Then we have an immediate layer transformation. And the immediate layer transformation is required because of people optimization or other optimization proposals, dependent on the implementation. Then the sequence is compiled to direct treated code, and instructions in between are bundled and are replaced with the addresses of the primitives which are executed. So within this simple scheme, it's possible to execute at base 4 up to 8 static operation bundles within a single interpreter iteration, and that's quite efficient. So the Niagara either allows very efficient and very high performance interpreters. Yeah, the operation code format allows unlimited static bundling of multiple operations to single instructions, which guarantees a high performance. It's also possible to implement software pipelining in an efficient way, and I can show you this. So it's a Niagara interpreter, not for the current either, but for test either. Anyhow, it's the same thing. Oh, sorry, it's the false. Okay. So basically, that's interpreter. So at first I cache here the register set, real registers, dependent on the C compiler. And then here I define, this code defines 2 arrays holding the primitive routines. And as you can see, these routines combine multiple instructions. So here 3 combined. The current interpreter I implemented combined 4 instructions. And that's all. That's a complete interpreter here. So I have a DTC stream, and all which is done is here to address the primitive array and translate 4 instructions, following 4 instructions to an address, and this address is then executed by an indirect branch. The routines here themselves are otherwise defined. Those are macros. And within these routines, the following steps for execution of the next instruction bundles are done beside execution of the actual instruction bundle. So this implements software pipelining. Software pipelining is an efficient method for the utilization of the different functional units of a superscalar out of order architecture like recent Intel processors. So this simple interpreter here is very efficient, such efficient that some micro performance test shows that it's for some tests no real difference to compile code visible. Yeah, the complete interpreter dispatch overhead is completely compensed. So this is a very efficient interpreter. Okay. So then for an ahead of time compiler, the same scheme applied. We have a core synchronization step, so serialization. POSIX treats, for example, require serialization if I execute multiple interpreters treats, because otherwise shared memory accesses are not possible, or are possible, but the stored values are not determinate. We have a fetch stage, required, of course, then also the immediate layer transformation for optimization purposes, and then the complete operation code or operation code sequences are at runtime compiled to native code. Yeah. Before execution, and this native code is then simply called. I've implemented this, and it was not very hard. I think I required 1 day to implement a simple ahead of time compiler for this ISA. What I recognize is that the execution model allowed time and memory efficient transformations of stack to register mapping, simple by a counter. Yeah. Some register contexts are stored to registers, and before in the compiled code then just increment counter. So the compiler increment a counter, the counter select a register, a processor register, for which the following instruction sequence is compiled. That's very simple, but that was very simple to implement, and the resulting machine code was very efficient and looked really optimized. So within the simple scheme, it is possible to entirely transform stack to register accesses, and instruction bundling also simplifies the optimizing compilation, because people optimizations can be done at the IL stage. The IL stage is nothing more than stack representation, which allows shuffling of instructions for specific optimizations for in-order designs, like the Intel processors, for example. That works quite well, and the generated machine code was very performance even on these in-order architectures. The low instruction count means that the porting effort is really low. I need something about 22 instructions. or instruction routines, which need to be ported to different machine code, and this machine code is incorporated, simply copied to a machine code stream, and this machine code stream is then executed, and in between compilation was as I noticed before, optimized. This resulted in a really high performance, even on in-order designs. So typical ARM processors have tested the generated machine code was high performance, and I'm very happy with the results. I have a hardware implementation, prototype hardware implementation, which I created with help of the Freie Universität Berlin. And if you take a look at this simple operation code format, this packet operation code format, you see the possibility to combine all of these instructions here, inclusive here the IREP slot, because the control sequence is determined before the execution. And this means that all of this instruction, because of the stack architecture, depend on each other. Yeah? So one instruction which addresses stack is a requirement for execution of the next instruction, and so on. Okay, I doesn't think that's a disadvantage, but I went this to an advantage, because if all of these instructions depend on each other, we have a single instruction stream which modifies a single data stream in time. And this allows a very efficient way to execute entire operation code sequences, because operation codes can be transformed into a control and a data stream, and both streams then simply can configure an energy optimized complex programmable logic array. Yeah, they are simply bit streams. This allows to execute entire sequences of operation codes, operation code sequences within a single clock cycle. Simply the decodation stage generate from the operation code directly control and data streams, configure a simple FPGA. And these FPGAs then, in time, within a single clock cycle, execute the data stream. So the prototype architecture here, the prototype implementation, is able to execute 3 operation codes, so 36 operations within a single clock cycle. And all of these 36 operations are basically fused into a single instruction. And that means it's a missed processing engine, because we have a multiple instruction with modify a single data stream. I think that this is except for the Stolic arrays, the only real implementation of a MIST processor, which I know. Yeah, I think the result is quite nice, and I think it's one, if not the only way, to implement very high performance efficient stack processors. So this was my little talk, and I hope you have understand me somehow. And yeah, that was it.
Were you waiting for me to talk?
Yes, I hope someone have understand me.
Up, up. Wrong way, wrong way.
So I think I was talking with you and maybe others about the gray code addressing, which you mentioned in your talk. And I'm wondering what the address decoder looks like for that. I don't know whether you have done the address decoder for the gray code addressing or for instructions, what that looks like in like a combinational circuit or something, whether it's simpler than a binary addressing or a binary decoder, whether it scales better.
Okay, it scales better, but I simply have made following. I have here a dissertation read it about oh about a quite similar instruction coding to my one, which I choose, and I simply take this instruction encoder was were published in this publication and modified this by experimentation for encoding gray code. And I found that the resulting decoder is something about 20 or 30% smaller than the result than a equivalent binary encoder.
Oh, cool. It's good to
Yeah.
good to
But
good to see.
that's simply a result by experimentation.
Yeah, I read in the paper that I think I posted on Reddit. My name is Point Free on Reddit, by the way. And I read in the paper that there's like 70% fewer bit switches with gray code addressing versus binary addressing, and that saves a lot of current consumption because
Not really. 20, 30%.
20-30% simpler, but bit switches, number of bit switches when you're addressing with gray codes versus binary.
Well, I'm sorry, my English is quite bad, but I hope you can understand me.
Yep.
Because say it, gray code simplifies encoding because each bit, yeah,
Yep.
of each bit position is a single bit position. Yeah, there exist
Yes.
no multiple bit positions within the binary format, and you can take this to advantage by combining logic circuits. Okay, simply.
Yeah.
You just you just get you just need to
Shift left.
recycle the control signals.
All right. Yeah.
Yeah, and this lead to a lesser cycle count between 20 and 30%, but not more.
Oh, in terms of cycles, yeah.
Yeah.
Yeah. You're just shifting by one to shifting over the address to decode it. Is that how you do it? You shift by
Yes.
one each time to decode the address?
By shift, yeah, okay.
Yeah.
Simply by shifting, yeah.
Yeah.
Okay.
Thank you.
Yeah.
The Zilog Z80 processor, you know,
Mhm.
this
Yeah.
this early processor had a 4-bit A loop, okay,
Yeah.
and it was an 8-bit processor. They had implement something similar, and you can get a complete, very sophisticated simulator somewhere on the net on www.502.org. And if you zoom into the gate level, you can see something similar what I have implemented for the gray code encoder, but in this case for the A loop.
Yeah.
Yeah. So as tip, get to this web page and experiment here, execute some Z80 machine code, and you can see how they implement something similar by reusing control lines.
Yeah.
Yeah. Uh, that's a really simple approach, I think, and that was a reason why I choose gray code.
Yep. Great.
Oh.
Okay.
Thank you.
Okay. Any other questions? No. Well, thank you very much, and I think we got lunchtime. And so we will talk to you later, and hopefully you'll be able to see this and post it up soon. Thank you very much.
I think that you can understand me.
Mostly
Mostly.
you did real good. Your English isn't that bad. It's not as bad as my any other language.
Okay. So,
Thanks a bunch.
okay.
Okay.
Um,
I'll shut this off.
yeah.
And we will be back after lunch. We'll shut this whole thing down. Thanks a bunch, audience.